And now, is it possible that these two subsystems go up and down similarly, or their distribution actually is very similar, very identical? Is it possible? It is possible, let's say, if the raw material for a part is coming from the same supplier and you don't know about it. It is possible that that you have got one part, or let's say multiple parts going through one supplier who's using the same process for everything, right? And you may not know about it, right? So the idea is that your system output may no longer be normally distributed. So what happens? In that case, you continue to add cost to fix your product. Because when you're trying to deliver a product and you expect to be this to be plus minus 6, this to be plus minus 3 sigma, you should have no cost, because that's how the system was designed. But if you are here, all of this is going to add cost to you. Does that make sense? See, we think about tolerance stack up, right? We can think about tolerance stack up. Now, think about process stack up. And that is a concept where you are thinking for, are there multiple subsystems or components who are correlated with each other? And consequently, your output is not going to be normally distributed. So when you finish your system and when you begin to get output from the system, and you begin to collect data, and it's not normally distributed, what do? How do you go about fixing that problem? One way is you're going to go and check, and you're going to say, okay, I'm going to see what are critical components, and I'm going to check tolerance of each part. That's the standard engineering approach. Am I correct? The standard engineering approach. I want to check tolerance on every component. But that doesn't fix the problem. Because it may fix a problem on one product you produce, but what happens to the population? And here it is about the population. It's not about getting one prototype to work, it's about getting the population to work. So, and the only way to make sure that the population is going to work reliably is, of course, most of the time you have got vendors who are already qualified and you are happy with it. You may have long tradition of processes which have been built, but when you are going for new product development, developing new suppliers, it's going to be very difficult to see that your product, first release, is normally distributed. And sometimes, even after producing a great many lots of products, it may not be normally distributed because that critical factor, process stack up, you don't think about it. Okay, so with that, I want to leave you with that talk is think about statistics in later stages of product development and incorporate that information. There is ways to incorporate this information in PSpice. You have choices of Monte Carlo, worst case analysis, and then you have also parametric sweep, which can be to great advantage. And again, you don't need a whole lot of information. You just need little critical information to be able to simulate it. Here is an example for a brushless DC drive. Right? You have electrical variables. So resistance coil ABC, back EMF coil ABC, Hall sense of timing ABC. Now, this is from real experience. See, what happens is, when the process is not normally distributed, in electric vehicles, you feel it. Because you feel the vibration of the motor. You feel the torque variation of the motor. I mean, in a drive where you're not sitting on it, you may not realize it as much. For example, one of the products we had released was an electric bicycle. Now, this electric bicycle is costing $4,000, right? And it becomes critical at that point of time because people feel it. When you're riding a bicycle and you have a system, even with a slight variation, and when you're producing thousands of these, you don't want to tweak each and every bicycle. So here you have got all of these variables on your plate to analyze. You have got, so if you're familiar with BLDC, you basically have quite a great deal of products, variables to analyze. Of course, I think you can eliminate most of them within a short period of time and focus on critical parameters. You can verify, okay, everything is normally distributed, and then you can begin to get to the bottom of it on parameters which don't have normal distribution, and then you begin to see if there's a correlation between them, if there's a process stack up between them. Okay. Now, I'm using a statistical term, exogenous and endogenous variables. Basically, these are, for the sake of simplicity, independent variables. And endogenous are dependent variables, right? So, independent variables would be something which is essentially you have no control over. And then these variables depend on this, right? So when a supplier is giving you a part, it's coming into your system, you could characterize the tolerance on that part as exogenous variable. And then, of course, you can run worst case analysis using exogenous variables and associated probability distribution. All right, that was conclusion of part one. And any questions I can answer? I'd love to field at least one or two. Let's see here.
I'm sorry for being late. Myself, Surya Narayana, I'm a faculty in the Department of Energy Science and Engineering, IIT Bombay. So I work in the area of power electronics applications to power systems.
Circuit simulation, device modeling, parameter extraction.
Thank you for joining.
Meghnad Shah, an electronics engineer and an industrial outfit in Pune.
Thank you. Thank you for joining us. All right. We have, thank you for coming today, and let's get into, we have a break at 10:30. We're going to get started with this session. And here we're going to do a few demonstrations, and then we're going to talk about some tools in the kit, which we have provided on a CD, and we go from there. All right. Now, in this session, we'll do a review of PWM schemes. We talk about, we'll also talk about high side PWM, high and low side PWM, all channel PWM, and then large signal model. And then we'll have 6 demonstrations. Okay, that's what we will cover. So in the PWM schemes, BLDC driven mainly, these are the 5 methods. This is not all inclusive, but these are the 5 prominent methods you drive BLDC motors with. So you have high side PWM. So you're only, so if I draw the circuit for a BLDC motor, we're talking about six switches, and you have a DC bus, and basically you have a 3-phase motor here, which is feeding from 3 points, A, B, C, connecting to A. And then of course you have got control system and all that good stuff there. So BLDC, so we're really talking about that particular topology, where we've got 6 switches, they're configured in 3 phases, and we are only PWMing the top switch, only this switch is PWMing. So we're switching, we're only PWMing this part. Okay? That's all we're doing. And method B is high and low side PWM. So when you're conducting a current, essentially when you're conducting a current, you're conducting a current, so you have, you can think of it as having 3 coils, 1 coil, 2 coil, and 3 coils. And when I'm conducting a current, let's say I'm turning this on and this on, right? So here, in this case, you do high and low side PWM. Okay, that's method 2. And method 3 is also high and low side PWM, but now you have got 2 top switches and 2 bottom switches. Okay, and then you have got the method D, where you also have high and low side PWM, but you have got low side shifted by 180 degrees or half the cycle. That effectively increases your switching frequency, and so that's another method. And the last method, E, is all switches PWM at all times. So those are the 5 methods we'll be talking about. And this is a very brief comparison of various methods. Now, you use method A, high side PWM, when you're trying to build a very low cost drive, and you have got a very low power drive, low cost, low power drive, you use method A. You know, you have so that's a cost sensitive part. Then if you look at conduction losses, in this particular, this is for a particular drive system, least in C and E. Efficiency is best for D and E for low inductance, high current motors. And bus capacitance requirement is highest for B and C, at least in this particular case. This may not be true for all drives, because you'll be able to The idea would be that when you are developing a drive, that you are able to simulate all 5 methods and determine which method is best for your drive, because it depends upon the drive parameter. This is expected back EMF voltage, right? So this is it doesn't mean that you cannot still use BLDC for sinusoidal distributed motors, but normally when you talk about BLDC motor, you have a back EMF which is trapezoidal. Okay, you have, and then A, B, and C are all 120 degrees distributed, delayed from each other. And then you are assuming your current injection to be flat. You basically are injecting in phase with your back EMF voltage, right? So phase A current is in phase with EMF, back EMF A. Phase B is with B, and phase C is with C. So that's the idea behind it. So these turn out to be DC values, essentially, when you multiply them, because power is only being transferred when you multiply I and V, this is the power output, which becomes essentially a DC output. But in reality, it's a different case. You end up optimizing alpha because of manufacturing variations. You end up optimizing beta, and you end up optimizing, of course, that is control over the magnitude of the current. So that's the any question on this one? This would be pretty basic. Now, to drive the top side PWM, you essentially have 3 Hall sensor signals, HA, HB, HC, and the way you line them up, essentially in the rotor, you have this code which is developed. So Hall sensors essentially will take 6 positions, 1, 2, 3, 4, 5, 6 positions. So when they give you every position, based on that, you are able to drive your top switch. AT refers to your top switch, BT to the top B switch, and CT to the top C switch. So you have leg A, leg B, and leg C. So based on Hall pattern, you figure out, so in this section when you have 1, 0, 0, you have A top and B bottom. So if you look here, so if you look here, 1, 0, 0, so you say, okay, I have got current in A top and B bottom. So that's what this is supposed to show you. Then at 1, 1, 0, you have A top and C bottom. So you go to 1, 1, 0 section, and you say, okay, in this section, I have got A top and C bottom. Right? So this is how, based on your current requirements, you have matched up your Hall sensor signals, and all it is once you have this figured out, you basically issue a logic table to drive your BLDC motor. And the dotted line is supposed to represent the back EMF voltage. So you know that your current is matching with the back EMF voltage, and so your output power is comes out to be DC value. And the torque, if output is a DC value, then torque, of course, we expect to be just that by that, speed of rotation. And then if they're all equal, then you can just write that. So torque is equal to that divided by omega. Okay. Any questions so far on this one? All right. We have got 4 more minutes. Let's see. Now, so in simulation, what we have done. Let's talk about the first PSpice circuit we're going to show you about. Now, what we have done is we have built the circuit. This is, and here we have we have 6 ideal switches and 6 ideal diodes. And all of these are convergence robust, that we don't want any convergence issues, right? So, and I'll show you the sub-circuit, or show you the sub-circuit we have used to develop these switches and these diodes. We'll show you in a minute how the motor model is. The motor model is essentially a simple implementation to show trapezoidal back EMF voltage.